let's move on to equilibrium. Equilibrium is known as special type of motion of an object. So when object is in equilibrium, you can take the component along x-axis towards left and right should be equal to each other. And the other thing is the algebraic sum of component along y-axis should be 0, which means the addition of component along y-axis towards upwards and downwards should be equal. And the other thing is, when taking moment around any point, the clockwise moment and anti-clockwise moment should be equal to each other. Okay, let's move on to this example. So you are given P, Q and S. This is given as 30. This is also 30. So when the object is in equilibrium, what you have to consider is the component along x-axis towards left and right should be equal to each other, which means P sin 30 should be equal to Q cos 30. P sin 30, that is half Q cos 30 root 3 over 2. So what happens? P equals root 3Q. When considering component along y-axis, what happens? P cos 30 plus Q sin 30 should be equal to S. Cos 30 root 3 divided by 2, sin 30 half equals S, which means root 3P plus Q equals to S. Those are the relationships can be taken when object is in equilibrium. Okay, let's consider equilibrium of object under two coplanar forces. Let's consider F1 and F2. So here you are given F1 is greater than F2. So what happens there? The resultant is there. The magnitude should be F1 minus F2 because those two forces are parallel, but the directions are opposite. So there is a resultant. Therefore, you can't take the object is in equilibrium. Okay, so what would be the adjustment in order to get the resultant as 0? What would be the adjustment? So the adjustment should be F1 and F2 should be equal to each other. What happens? So the resultant getting 0. But there is a problem here because here this case is known as couple of force, which means there is a torque around each and every point. Therefore, you can't take the object is in equilibrium under these two forces, which means we need to modify these two forces further. So you can consider these two forces as just like this. Then what happens? Resultant gets 0 and the other thing is the couple of force is also 0. Then we can conclude the object is in equilibrium under these two forces, under these two coplanar forces. So our conclusion is when object going to be in equilibrium under two coplanar forces, those should be equal in magnitude, opposite in direction, same line of action. That is our conclusion. Okay, let's move on to the equilibrium of an object under three coplanar forces. Here there are two instances. One is forces are parallel with each other. Let's consider F1 and F2. So if you are given that F1 is greater than F2, we know that there is a resultant such as F1 plus F2. It should be, the line of action should be towards the greater, and it should be in between two forces. So according to the previous theory, what happens? According to previous theory, so we got the resultant of these two forces as F1 plus F2, which means if there is a force like F3, it should be opposite to the resultant of these two, which means F3 is just like this, and the magnitude of that is equal to the addition of those forces. What happens? We can conclude the object is in equilibrium under these three parallel forces. That is our conclusion. Okay? Right, so our conclusion is, in order to get the equilibrium under three coplanar forces, when they are parallel to each other, the one force should be equal to the resultant of any two other forces. Resultant, the opposite, the direction should be opposite, and same line of action, magnitude, should be the same as the resultant of any two forces. Let's move on to the next one, B part, that is equilibrium of an object under three non-parallel forces. So if F1 and F2 is just like this, and if you are given as F1 is greater than F2, first of all you have to get the resultant of these two. Just like this. So this gives you the resultant. The third one, I mean the F3, should be opposite in direction, magnitude, the same magnitude, and same line of action. So we can conclude F3 should be equal to the resultant of F1 and F2. Then we can conclude, when object is in equilibrium under three coplanar non-parallel forces, three forces should be met at a point. That is our conclusion. Let's move on to triangle theorem. Triangle theorem and Lamys theory. So, in order to check the resultant of three coplanar non-parallel forces, we need to make use triangle method. Triangle theorem. So here, first of all, you have to get the scale in order to graphically interpret these three forces. For example, F1 should be graphically interpreted just like this. So if you take the angle between F1 and F3 as alpha, beta and gamma, what you have to do is, so you have to, when you graphically interpret the force like F3, you have to take alpha angle towards clockwise at the end point of F1. End point of F1. So this is F3, this is alpha. Then what you have to do is, again you may have to use a protractor in order to measure beta angle, in order to measure angle beta. So this should be the beta and this is F2. So here what happens, the initial point and the final points are coincide with each other, which means there is no resultant. There is no resultant. So how would you mark the angle like gamma? So gamma is the angle in between F1 and F2. So F2, this F2 is parallel with this. So then you may have to extend F2, then take the angle. This represents gamma. This is the way of marking gamma. So our conclusion is, since the triangle is completed, we can conclude there is no such resultant given by these three forces, which means we can conclude object is in equilibrium. Let's consider the Lamys theorem. So when considering the Lamys theorem, what you have to do is, you have to select a particular force such as F1. Then you have to take the angle in between other two forces like beta. Then take the sign value. That ratio should be constant throughout the situation. So when considering F2, what happens? Take the angle in between F1 and F3, that is sine alpha. Then you have to consider the final force like F3, the opposite angle or angle in between F1 and F2 is gamma, sine gamma. This is the Lamys theorem. Okay, let's consider the previous question. So this is P, this angle is 30, this is Q, this angle is 60 and this is S. If the object is in equilibrium, how would you apply Lamys theorem in order to get the relationship between those three? So when applying Lamys theorem, each and every angle around this point should be known. This is 90, this is 90, which means the angle between P and S is 120. Angle between S and Q is 150 and the remaining angle is 90, that is angle in between P and Q. So according to Lamys theorem, P should be divided by the angle in between Q and S, that is 150. P divided by 150. It should be equal to Q divided by sine 120 and s divided by sine 90. So we know that sine 150 is equal sine 30, that is 1 over 2, 2 goes up, and sine 120 is equal to sine 60, that is root 3 divided by 2, again 2 goes up, so 90 is 1. So now we can take 2p as s, which means p equals s divided by 2, as well as 2q divided by root 3 equals s, which means q equals root 3 s divided by 2. Those are our conclusions. Let's move on to types of equilibrium. There are 3 equilibriums. Equilibriums are known as stable equilibrium, unstable equilibrium, and neutral equilibrium. So this can be named as unstable equilibrium, which means when you give some small displacement, what happens? It is getting unstable. It falls, which means the initial equilibrium is unstable. Considering this, we can conclude the equilibrium of object is stable, because when you give a particular displacement, what happens? Then releases. Then what happens? It comes back to its original position, which means the initial equilibrium is stable. So here what happens? This is a kind of a neutral equilibrium. This is the initial stage of the object. Then a small displacement is given by us, then it releases. What happens? It is again approach to the equilibrium position, which means this is neutral equilibrium. Now we can consider a system just like this. A man is on the bench at the center of gravity. Let's take the weight of the man as 200 newtons and weight of the bench is 600 newtons. So according to the symmetric of the figure, so the R value should be equal to each other. So we know that if the object is in equilibrium, the upward force should be equal to downward force. So upward force 2R, downward force 800, so R equals 400 newtons. And we can further conclude, when this man moves towards right, which means towards point B, what happens? This normal reaction increases while the other decreases, but the addition should be the same as 800 newtons. Should be the same as 800 newtons. Let's consider another example. Initially, a man is at the center of the bench. So the weight of the man is 600 newtons and the weight of the bench is 200. So we know that according to the symmetric, this should be 400 newtons. 400 newtons. So actually here you have to conclude the minimum tension in the string. So you have to calculate the minimum tension. So what would be the rather maximum tension recording in the string? So here we know that the tension in the string is 400 newtons. So if you conclude this tension as maximum, there is a problem. What happens when this man moves towards right? As we conclude in the previous case, this tension increases while the other decreases, which means tension in the string, the right string, greater than 400, so it fails. So actually we have to consider the tension in the string when man close to the right end. So here we know that there is different tension like T1 and T2, and the weight of the man is 600 while the weight of this one is 200 newtons. Now you have to calculate T1. The system, since the system is still in equilibrium, you can get the moment around point B. So what happens? Taking moments around point B, so there is anti-clockwise direction, anti-clockwise moment and clockwise moment. So T1 should be multiplied by 2L, while 200 should be multiplied L. So T1 equals 100. T1 equals 100. So what happens? T1 equals 100. You can't take the maximum tension in the string as 100, because we conclude that the man at the center, the tension was 400. So you can't take your answer as 100. The other tension should be the answer. What would be the other tension? That should be 700 Newton. That is the maximum bearable tension in the string. Okay, let's move on to this case. We have to consider limiting equilibrium. So here we know that two forces there, one is weight, the other one is normal reaction. The normal reactions given by the horizontal plane is equal to each other. So the resultant should be just like this. So we can conclude, since the object is in equilibrium, R equals mg. Now we have to consider the plane is inclined at an angle of theta. So the weight is there, but you can't take the normal reaction as the same. Normal reaction varies just like this. just like this, and there is a friction also. My question is, what would be the line of action of these normal reactions? So in order to get the answer, you can consider there are three coplanar non-parallel forces act on this object. What are those? One is weight, the second one is friction, third one is the normal reaction. So if you don't have any idea about the line of action of normal reaction, what you have to do is the non-forces. You know that the direction of two forces. So those two non-forces, the line of action of those two non-forces should be met at a point. So that meeting point is here, that is friction and the weight. So we can conclude the normal reaction should be just like this. That is the line of action of normal reaction. That is our conclusion. We can further consider the system is in limiting equilibrium. So here what happens, this is the line of action of weight and this is the friction. So this is the coinciding point of line of actions of weight and friction. So the direction of the normal reaction should be just like this, in order to get the equilibrium under these three coplanar non-parallel forces. So this point should be the coinciding point, and we know that when an object is in equilibrium under three coplanar non-parallel forces should be met at a point. So this is 90, this is 90 minus alpha, again 90 minus alpha, this is 90, this is alpha. Now we can consider the normal triangle just like this. So this is radius of the base and this is the height. So actually that is the gap between the bottom and center of gravity of the object. So we can measure that angle. So we can take the tan value, tan alpha equals R over H, which means alpha equals tan inverse R over H. In order to increase this angle, what you have to do is R should be increased while it should be decreased. So in a formula vehicle, we can observe this relationship, which means they are not going to be collapsed because the height of the vehicle is very small respective to other vehicles and the radius or area of the base is considerably high. Therefore, R increases, H decreases, alpha has a considerable value.